Still sits here. You don't need to stand. Okay, let's start. It's my great pleasure to introduce today's speaker, Professor Louis Ho. So Professor Ho got his PhD degree in 1995 from UC Berkeley, and after that he got awarded the CFA postdoc fellow in Harvard Smithsonian Institute for Center for Astrophysics. And from 1998, he became a staff astronomer in the Carnegie Observatories in Pasadena. And just from this year, Professor Ho became the director of the Kavli Institute of Astronomy and Astrophysics in Peking University, and at the same time also the chair professor of the School of Physics, and also distinguished research fellow of the Chinese Academy of Sciences. And Professor Ho is an expert in supermassive black hole in galaxies, and also interstellar medium and star formation in galaxies. So it's really my pleasure to welcome him and to give the joint colloquium today on the topic of black holes and impact on galaxy formation. So let's join me to welcome the speaker.
Is this microphone on?
No.
That's great. You hear me? Well, it's a real pleasure to be here back in Taiwan. The weather and the air here is much better than in Beijing. I'm always apprehensive about giving joint talks in the physics department because you guys are supposed to be much smarter than astronomers, so I never know what to say to you. And also, whenever physicists think of astronomy, they think of the universe in a very simplified manner. Most physicists view the universe during the epoch of recombination, when the universe was mostly smooth to 1 part in 10 to the 5, when the universe was only 300,000 years old or so. And other physicists, when they work in astronomy, they work in an even simpler state. It's called the era, the Dark Ages, when there's absolutely nothing to be seen, and the physics can be as simple as you like, just hydrogen, mostly. And if you're a little bit more ambitious, you work on the epoch of reionization, when you form the first generation of stars and perhaps the first generation of compact objects that might become quasars and eventually galaxies. However, as an astronomer, I'm mostly interested in the universe 13.7 billion years later, when it's much more complex. You see a universe full of galaxies of many different types, from relatively simple massive galaxies such as ellipticals, where the structure is relatively uniform and you have old stars, to objects where it's essentially very diffuse, simple exponential disks, to more complicated objects that have bars and bulges and many types of substructures. And the mystery to most of astrophysics who think about galaxy formation is how did the universe evolve from that extremely simple state to this obviously much more complicated diversity in baryonic structure after Hubble time of evolution. And a big clue of how this happens is by staring very deep at the sky. This is a picture of the ultra-deep field observed with the Hubble Space Telescope. This is one of the deepest images we know of the universe. And it's essentially an archaeological record of what has happened since the epoch of galaxy formation. And when you zoom in into this rich data set, what you see is that the galaxies come in many different types. Some already have shapes that you can recognize as nearby galaxies, but others have these very strange shapes that seem to be interacting, that seem to be in morphologies that we do not recognize locally. And because the universe was much more crowded back then, galaxies have the opportunity to bump into their neighbors, they interact, all sorts of hydrodynamical effects come into play that drive many types of phenomena that we see associated with galaxies. This is the view when you look at the stars. However, if you put on X-ray vision, the universe looks rather different. This is an image taken with the XMM Newton satellite of the same patch of the sky. We're recording only high-energy X-rays. And what these X-rays are coming from is mainly accretion into supermassive black holes in objects we call quasars, that we call active galactic nuclei. When you look at the global energy budget of the universe, okay, so this is a plot of energy versus wavelength or energy. Okay, most of the stuff comes out due to stars, from reprocessing of stars, from starlight. There's a cosmic microwave background. But this bump here comes from the cosmic X-ray background, the bulk of which, at least in the hard X-rays, comes from the cumulative emission, the energy, total energy density of black hole accretion. So we know that black holes play a significant effect in the life cycle of galaxies. We now believe, after many decades of research, again, that this energy ultimately derives from gravity. As material falls in to the central gravitational potential of a black hole, it releases the gravitational energy in the form of radiation, in the form of kinetic energy, in the form of momentum. As I'll describe later, this energy, in fact, appears to be extremely important for the large-scale evolution of the galaxy and even clusters of galaxies. And the culprit behind all of this are these quasars, or active galactic nuclei. Okay, so all of you may know this. Okay, so this is a typical optical UV spectrum of a quasar. It's extremely blue. That's because it's hot. It's hot because it's material falling deep into the gravitational potential well. Okay, and you have these many emission lines arising from metals that are excited. And in particular, these emission lines are very broad. That's because they're moving around at very large velocities, circling around the black hole. This pointer is coming apart again. In the last decade or so, we've developed techniques to estimate the masses of those black holes. This is a plot of black hole masses versus redshift for a sample of quasars. And you can see from the y-axis that out to redshifts of 4, 5, 6, and now even 7, black holes at those times already reached extremely high masses, 1 billion and even 10 billion times the mass of the sun. Looking in detail at these high redshift quasars, they're really remarkable. Okay, so this is a plot of one of the highest redshift quasars at a redshift of 6.4, when the universe was only 800 million years after the Big Bang. Not only do you see all these metals, okay, so these lines come from ions like carbon, silicon, iron, magnesium, when the universe was only less than a gigaeuro. But you can see, in fact, that they have these enormously broad emission lines, which we have now proven comes mainly from gravity, and that they reflect the bulk virial motions of the gas around the black hole. In this case, this black hole has a mass of 3 times 10 to the 9 solar masses. Again, when the universe was less than 1 billion years old. This type of activity was very common back in the heyday when the universe had redshifts of, say, between 2 to 4. Okay, that's when the space-sensitive quasars peaked. By redshift of 0, which is where we live now, there are no quasars. So we know that these quasars, because gravity only grows objects, that there should be massive black holes that are locked up in the centers of present-day galaxies. But they are dormant. These black holes once used to shine as quasars. Today, they're basically asleep. They're quiescent. Okay? So this type of hypothesis was already speculated by many people, including Saltpeter, including Lyndon Bell, back in the 1960s. The challenge for astronomers is to go out to look for these objects in the nearby universe. And by far, the best evidence comes from none other than the center of the Milky Way, where detailed proper motion studies of stars within the central, very central region, this is 0.1 arcsecond indicated here, over many years, more than a decade, has been able to track the orbits of a handful of stars. Okay? One of them goes around at velocities of about 2,000 kilometers per second, in fact. And by simple modeling of these orbits, you can deduce that the center of the Milky Way has a black hole with a mass about 4 million times the mass of the sun. Not only is the mass high, more impressive is the fact that all of this stuff is jammed within a radius of basically about a light week. Therefore, the mass density of this material is close to 10 to the 12 solar masses per cubic parsec. This density is so high that effectively you can rule out all astrophysical alternatives to a single supermassive black hole. There is no cluster of astrophysical objects that in fact can survive over reasonable timescales. Okay, so even though we haven't yet seen the event horizon, that's one of the goals of one of the projects in Taiwan in the future is to actually see the event of horizon of a supermassive black hole. For astronomers, this is already very good. Okay, we've been able to measure a dark mass confined to an extremely tiny volume. Beyond the Milky Way, up until recently, the best evidence comes again from radio astronomers. This is from VLBI observations of so-called water megamasers that can achieve milli-arcsecond resolution. This is a nearby galaxy, NGC 4258, only 6 megaparsecs away. And you can trace these maser spots, which seem to define a very thin disk in the plane of the sky. And because it's an emission line, it's a maser line, you can measure its velocity, and the velocities track an almost perfect Keplerian rotation curve. Okay? And in this case, it has a black hole mass roughly 10 times that of the Milky Way. And again, it's confined to an extremely tiny volume. Okay? This is scale is in parsecs. This is 0.1 parsecs. Those, until recently, in fact, they still stand as the two best cases for supermassive black holes known in astronomy. But the bulk of the statistics did not come from these observations. They really relied on the Hubble Space Telescope. When HST's aberrated optics was repaired in the mid-90s, this was one of the key science drivers for the HST, we began to take data in a frenzy. And the early observations relied on detection of ionized gas. This is H alpha, where, okay, so this is a velocity, receding, approaching, and this is distance from the center. And you see this characteristic velocity rise to the center, which you can naively interpret. If it's due to gravity, you can derive a black hole mass. In this case, the mass is about 10 to the 9 solar masses. Those were very early observations. Later, we became a little more sophisticated. We can actually map out the velocity field in a two-dimensional way and actually get the full velocity field and get more robust mass constraints. Okay, so this is one major technique that HST has contributed to this field by mapping the gas velocity field in ionized gas around nearby galaxies. Another technique is also very powerful, which is not to look at the orbits of the gas, but to look at the orbits of the stars. Most of the work was done by this collaboration called the Nuclear Team, where we basically systematically, over a period of about 10 years, surveyed very large samples of objects with HST to map out the stellar kinematics. And what we discovered as we did this systematically is that basically there were black holes everywhere. To be more specific, every object that we looked at that had a bulge, that is a galaxy that has a central concentration of stars, a bulge, okay, had a black hole. It was not a single case that had good data where we failed to detect the signature of a massive object that we interpret as a black hole. And by about 1998, we have enough objects we can begin to look for statistical trends. And the trend that first really surprised us, and in fact surprised many people in the community, is that if you plot the mass of the black hole versus the mass of this bulge component of the stars, there was a very tight linear correlation. The more massive the bulge, for example, here's an elliptical galaxy where it's all bulge, okay? Here's the Milky Way that has a bulge in the disk, the more massive the black hole. The correlation is almost linear, and the scatter was relatively small. This paper, very influential paper headed by Magorian, this is the infamous Magorian relation. A couple years later, we stumbled upon a correlation that became even more talked about. This is the infamous M-sigma relation, where instead of plotting the mass of the black hole against the mass of the bulge, we're plotting here the so-called velocity dispersion of the bulge. This is the random component of the velocities of the stars. This is the component that provides the pressure support to the bulge. Okay? And what we showed is that there is this, again, a very good correlation. Now, it may not seem like very good to you because you obviously can see quite a bit of scatter, but in fact, a large fraction of this apparent scatter is due to measurement error. The intrinsic scatter is in fact very small. Okay? I'm not going to get into specifics because that has been revised, but at the time that we published this in the year 2000, it was thought to be almost negligible. This became an extremely exciting result because this result is actually very perplexing. You might think that it's natural that something bigger should produce something bigger, but in fact, you can think about it for 5 seconds and realize this actually makes no sense. The black hole is supermassive, but it only contains 1/1000th of the mass of the galaxy. It's a supermassive black hole, but it's only 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 9 solar masses. The galaxy is 10 to the 10, 10 to the 11 solar masses. So gravitationally, this axis should not know about this axis. The time scales and the spatial scales are totally different. This is the saltpeter doubling time scale is millions of years. This is a Hubble time, right? Galaxies evolve in billions of years. The size scales here is tens of thousands of light years. This is a Schwarzschild radius, which is the size of the solar system. Why is it that this scale should know about this scale? In fact, this was so perplexing that over the years there have been hundreds of theoretical papers written. Literally hundreds. And these seminal papers from 1998, 2000 have about 8,000 citations. This is the type of interest that triggered, was permeated in the community. And it's led to many interesting new developments in galaxy formation. Okay? And I'll summarize those in a minute. But basically, over the last 10, 15 years, this is sort of the standard paradigm that has emerged. All bulges contain black holes, as I just told you. The mass of the black hole scales roughly linearly as the mass of the bulge, but it only occupies about 0.1 to 0.2% in mass. The mass of the black hole scales as the fourth power of the stellar velocity dispersion, this famous M-sigma relation. And it's widely thought that this M-sigma relation is much tighter than this mass-mass correlation. Okay, so that the M-sigma relation is really the fundamental relationship, whatever its physical origin. It's thought that there's no strong dependence on this correlation with galaxy type, with galaxy mass, with galaxy environment. But it's thought that this correlation, in fact, evolves strongly with redshift. I don't have time to summarize observational data, but over the last 10 years, people have been trying to observe this relationship farther and farther back in time. And the result that people have always found is that when you go to higher redshifts, in fact, the mass ratio between the mass of the black hole to the mass of the bulge goes up by a factor of a few, maybe even a factor of 10. This is widely claimed in the literature. And you can blame all of this stuff by a magic word that theorists call AGN feedback. Okay, so how is it that the very small scale of the black hole couples to the very large scale of the galaxy? Okay, the answer, or we are told, is that even though the black hole is small, it's accreting material and releasing a significant fraction of the rest mass energy. 10%, maybe 50%, depending on the spin of the black hole. Okay, so material comes out as basically, c squared, something times c squared. The binding energy of the galaxy is v squared, okay, hundreds of kilometers per second. Okay, so the ratio is huge. Therefore, the impact on galaxy environment, the host galaxy, should be catastrophic, should be very, very strong. And most of the theoretical predictions have rested on numerical simulations such as this, where of course the universe is envisioned to form galaxies via hierarchical mergers, for example in two gas-rich systems, which when they collide, the gravitational torques drive a lot of the interstellar medium to the centers of each of the respective galaxies, which if they contain a black hole, not only ignite a central burst of star formation, but importantly, very strong AGN or quasar activity. And that releases even more energy, which comes out in this green color. But the firework really, really happens when both galaxies finally merge and coalesce, where most of the gas is dumped to the center of the galaxy, where effectively a bomb goes off. Okay? That's how you give birth to a quasar. The quasar releases so much energy that it basically catastrophically destroys all the interstellar medium in a galaxy. That shuts off the AGN activity, it truncates star formation, it turns the galaxy red and dead, in technical language, puts it on the red sequence. This is how you quench star formation. This is the standard story for galaxy formation these days. You go to any galaxy formation cosmology meeting and you see this movie or some version of it, and these are the basic principles that is essentially in textbooks. Now, this is what happens during the epoch when most of the energy comes out as radiation, that is, when they're in a quasar phase. We know that a minority of these black holes, in fact, most of the energy comes out as kinetic energy, or more precisely as momentum. We call them radio loud objects, where they squirt out these relativistic particles. We see them as spectacular radio jets that all of our VLBI friends know about. Okay? They love to track and study the complex physics involved in these things. And even though the luminosity is not very high, again, the impact due to the kinetic energy, due to the momentum, in particular on the intracluster medium and the environment, is very, very profound. Okay, so these are, for example, MHD simulations of what happens to the jet as it squirts this material out to very, very large scale. This is much larger than the scale of the host galaxy. And we see these things, especially with Chandra. Okay, with Chandra, okay, not only do we know about these radio jets, which we have known for decades, but we actually see the impact that those jets have on the blue stuff, which is the hot plasma detected in X-ray thermal emission. Okay, you see these cavities that are displaced by the radio jets. And these radio jets and these radio lobes produce this very, very intricate structure that records basically the energy output from these radio jets powered by black holes. And it solves a number of very long-standing and I would say embarrassing problems in astrophysics. One of them, the so-called cooling flow problem. Okay? In big clusters of galaxies, this X-ray emitting thermal plasma should have a cooling time that is very short. In fact, you can calculate what the cooling time should be, and most of this material should be deposited in the center of the cluster in a cool form. That's why it's called a cooling flow, and they should be forming stars. You should detect it as CO, as H1, but nobody's ever seen it. Okay? People looked and looked and looked, and there are thousands of papers on this. Okay? Now the answer is very simple. Well, it doesn't cool all the way. It doesn't have a chance to because the AGN in the center reheats it. Okay? So this is the standard explanation now. Even more embarrassing is the fact that the mass function of galaxies, okay, the standard mass function of galaxies predicted by lambda CDM is this dashed line. Whereas the observed mass function or luminosity function of galaxies is this solid line or these blue points. You can see that without the help of this radial mode or jet heating, you absolutely cannot produce the Schechter function or the specifically observed mass and luminosity function of galaxies. at least for the upper end. You should be having many, many more of these massive galaxies than you actually observe. This is a major, major conundrum in galaxy formation. Okay, so either something is really, really wrong with lambda CDM cosmology, or you invoke this friendly, heating agent called radio jets. So the combination of this so-called quasar mode feedback using radiation and AGN jet heating at late times using radio jets, these are the two sort of standard recipes that I would say the large fraction of the galaxy formation community have embraced. Until now. So let me give you some recent developments. I won't talk about this in any detail. Most of the material I'm now going to cover comes from this annual reviews article, which is extremely long. It's 160 pages long. So I'm going to give you the briefest highlights, the most important points, where this basic picture has changed in many ways. Okay? Some of the stuff on very low mass black holes is discussed in the early annual reviews in 2008, which is still current. So for the students, you can go read this for your homework tonight. One of the most exciting recent developments does not come from HST. In fact, it comes from large ground-based telescopes, 8 to 10 meter class telescopes, using adaptive optics techniques and IFU integral field unit spectrographs. And the question that we wanted to ask for a long, long time is, are there black holes more massive than 10 to the 9 solar masses, a few times 10 to the 9 solar masses, which was the previous upper limit based on the HST studies? Well, there ought to be, because if you look at the highest redshift quasars, I told you, they have masses of 10 to the 10, a few times 10 to the 10 solar masses, but we've never found them. And if they exist in nearby galaxies, they should exist in these biggest galaxies. We call them brightest cluster galaxies. Okay? These are the most massive galaxies in the local universe that live in the centers of clusters. This is the Coma cluster, the richest, largest cluster in the local universe. That's NGC 4889. Okay? And this is an astounding result from a couple years ago by the Berkeley group, McConnell et al., and Cheng-Pei Ma, and others. The black hole mass is 20 billion solar masses. And now they've discovered many more such things. Okay, so this is a major contribution to the field in the last few years. In fact, by people who didn't used to work on this subject. And it took the power of these large telescopes, because HST is only 2 meters, after all. Okay, so this is an 8-10 meter class. You need to collect the photons to do this. Another very, very important recent contribution has come, again, from the radio astronomers, particularly people working in the LBI. This is the NRAO group. They've discovered a new sample of water megamasers. Since NGC 4258, the famous object discovered in 1995, there basically was a gap of, 20 years, okay? Until the GBT came along, they were able to discover many more bright masers, water masers, mega masers, and with VLBA, they've been able to map them. You can see, again, they trace very thin disks, okay, or disk-like configurations, which have velocities that trace, again, very, very close to a simple Keplerian curve. So you can derive very precise, very accurate, and also very precise central masses. Okay, so this is extremely important. And in this latest review with Cormandy, what we've done is basically assemble and reanalyze the entire literature up to 2013. And we revised these basic correlations between the black hole mass and the mass of the bulge and the velocity dispersion of the bulge. Okay? So the first thing to note is if you just eyeball this, they're both very nice and tight. In fact, it's not true, maybe this is a little bit of an optical illusion, it appears that the scatter is larger on the left than on the right, but in fact, formally, the intrinsic scatter is basically the same. Okay. But only if you concentrate on these black and red points. The black points